Hi, good afternoon, everyone. And thank you so much for joining the first of a three-part webinar series hosted by the Southeast Florida Regional Climate Change Compact, focused on increasing the understanding of the Compact's third update to its regionally unified sea level rise projection for Southeast Florida. My name is Lauren Ordway, and I'm a Senior Program Officer with the Institute for Sustainable Communities, an international nonprofit organization that works with communities in the United States, China, India, and Bangladesh to unearth locally driven and equitable solutions to the biggest challenge we face, global climate change. For nearly a decade, ISC has partnered with the Climate Compact to provide implementation support for its work. Since the Compact's inception in 2009, it is focused on aligning local government action to build resilience to climate change and reduce greenhouse gas emissions across the four-county region of Broward, Miami-Dade, Monroe, and Palm Beach counties. In the Compact's early days, the partners recognized that the diversity of local sea level rise projections was a barrier to achieving regionally consistent adaptation strategies and policies and effectively influencing supportive policies at the state and federal levels, and thus set out to develop a regionally consistent projection for the region. Since the projection was first developed in 2011, the Compact has released 2 updates to account for newly available climate science in 2015 and again in 2019 through the generous support of a technical advisory group consisting of scientific experts within the academic community, as well as staff from local, regional, and federal government. The Compact also publishes an accompanying report providing specific guidance for application of the projection, as well as information on the technical methodology used to develop the projection. You can find the report on the Compact's website. Taken together, the projection and guidance report are intended to assist decision makers in Southeast Florida to plan for and make decisions about sea level rise and associated risk based on best available science to help safeguard the people, communities, and natural and cultural capital, infrastructure, and economic assets that underpin a prosperous and resilient region. Today's webinar will help set the foundations and will focus strongly on the technical aspects that underpin the development of the projection, as well as how to use the projection curves in practice. While the projection is indeed a technical tool, frequently used to inform and design infrastructure, it's critical that we keep in mind why we develop and use the tool in the first place. The people of Southeast Florida are increasingly exposed to risks related to rising seas, and we know that these risks are borne disproportionately to frontline communities experiencing climate change first and worst due to existing inequities and socioeconomic disparities. People's lives, safety, daily movement, sense of community, and security are at risk and at the center of our efforts to plan for a more resilient future for all. Given this reality, while climate science is constantly improving, it's clear that waiting for scientific certainty is neither a safe nor prudent option. The policy decisions we make today are shaping the future of our collective coastal community and the lives of the people who call this place home. With this in mind, this webinar series is intended to be iterative with the content building upon itself. Therefore, we hope you'll be able to join us for the next 2 webinars in the series over the next 2 weeks, June 25th and July 1st, that will explore how the sea level rise projection has been applied in a number of examples of planning, projects, policy, and design across the region. The projection within the context of Florida's emerging statewide resilience policy and legislation, communicating about risk and uncertainty with communities, and the critical need for engagement and co-creation with frontline communities, and making the case for continued and equitable investments in adaptation. A few housekeeping notes before I turn it over to our first speaker. This webinar will be recorded and posted on the Compact's website after this session is over. All attendees are muted. If you have technical difficulties, please use the Q&A box and someone will reach out to you to resolve the issue. Please also use the Q&A box at the bottom of your screen to ask a question at any point during a speaker's presentation. And after each session, we will have time for Q&A. We will try to get to as many questions as possible, but given the number of attendees, we unfortunately are just not going to be able to get to all questions. Finally, a link to the agenda and our speakers' full bios and emails are provided here in the chat box for your reference. So without further ado, I would like to introduce our first speaker, Dr. Samantha Danchuk, Assistant Director with the Environmental Planning and Community Resilience Division at Broward County. Dr. Danchuk has been an integral county staff person involved in both the 2019 and 2015 updates to the compact sea level rise projection, helping to lead the process undertaken by the technical work group. Thank you so much, Sam, for being with us and for your ongoing leadership.
Absolutely. Good afternoon, everyone. Let's begin with an explanation of the relevance of unified sea level rise projection for Southeast Florida. So sea level has risen for thousands of years. For the past 100 years, water levels have been measured in Key West. This tide gauge has the longest record in Florida. The blue lines in this graph show the monthly mean average of sea level. See that it varies considerably month to month, across seasons, and year to year. To make the trend in sea level rise more obvious, the monthly data points are averaged across 5-year periods, and that's shown by the black line. The black line makes it easy to see that sea level rise is not linear. It does not follow a straight line path or even a smooth curve. Some years it accelerates rapidly, some years it stays the same about, and sometimes it can even decrease slightly before increasing again. Overall, sea level is about 11 inches higher in 2017 than it was in 1913, and this record absolutely confirms that sea level is rising. Quickly, I'd just like to explain mean sea level. You'll see on the y-axis, that is the elevation data that the data is referenced to. In general, mean sea level is the midpoint between high tide and low tide, but technically it's an elevation datum determined from an average of water levels measured during a certain 19-year period or tidal epoch. And the previous tidal epoch was 1983 to 2001, and the current tidal epoch is from 2002 to 2020. So I'd like to quickly highlight some of our concerns for sea level rise before really debuting and explaining the projection. So here you can see photos of overtopping of seawalls. Higher sea level results in higher tides, and these high tides that are occurring now and over the past 5 or 10 years that occur in September, October, November, and December have been overtopping low-lying land areas and seawalls. And any other coastal infrastructure that's below the elevation of the tide. Also, you'll see that water is getting inside the seawalls, and that's a result of the higher tide levels, higher water levels pushing down and actually driving water through the porous substrate, the porous limestone underground, and water comes up behind the actual seawall itself. And we call that seepage. Seepage damages the infrastructure in that it allows opportunity for corrosion of the metals that are inside stabilizing the structure. Every time the road base itself is inundated with water, it damages the road base, and actually the asphalt itself deteriorates over time. So you'll see that when you do drive to these endpoints where there's often flooding, you'll see that there's kind of degradation of the infrastructure itself because it's been repeatedly flooded. We are also experiencing disruption in our transportation networks. You'll see that for multiple portions throughout the day when there are these high tides, the water is actually coming over the walls, it's coming across the street, or maybe it's coming up drain pipes or up unprotected areas of land and actually flooding the streets and preventing people from being able to access their communities and from making it to work, and it disrupts our economy and the functioning of our local communities. Sea level rise is also causing the groundwater table to rise. So in Broward County, through extensive modeling efforts, we've found that for every foot of sea level rise in the ocean, you're seeing about a foot of groundwater table rise, in especially these red areas that are shown in the image. It decreases as you move further west, but for those areas in the east where the groundwater table has risen, there's a significant decrease in storage capacity in the soil, and it limits the amount of drainage that it can occur during a rainstorm. Additionally, it is causing saltwater intrusion into our drinking water. Our freshwater aquifer is contaminated by the saltwater that is being pushed in as sea level rise increases, and that greater ocean water volume is pushing against the freshwater aquifer lens. As sea level rises, it's going to intrude over land, right? So we know that inundation is a significant risk of sea level rise. We've looked at these vulnerabilities across the Southeast Florida region. So here we're just highlighting the portions of land that would be underwater for the predicted scenario under the Unified Sea Level Rise projection. And the areas in blue are areas that would be permanently wet, right? I mentioned that drainage will be decreased as a result of sea level rise, especially in our coastal and waterfront communities. We are projecting future rainfall to be even more severe than it is today. And when these storms occur, they'll have even less capacity for the community to recover after a flooding event. Sea level rise will also result in higher storm surges. So these photos are actually from Superstorm Sandy in 2012, but I could have shared photos of surge covering the Hollywood Boardwalk last fall. So areas that are not protected by dunes are vulnerable to storm surge and are increasingly vulnerable to added sea level rise. Essentially, the storm surges that occur often now will be even deeper in the future and more destructive. This graph shows the change in sea level in inches by decade. In the 1930s and 1940s, sea level rose about 2 inches per decade. In the 50s and 60s, it did not change much. Then from the 70s through the 2000s, it rose about 1 inch per decade. In the 2010s, the rate of sea level rise significantly accelerated, rising over 3 inches in a decade. This rise caught the attention of the community. During the highest tides of the year and storms, water levels were now high enough to flood over backyards and seawalls and onto roads and into neighborhoods. The news and policymakers started talking about king tides and nuisance flooding. It also provided a preview of what the first foot of sea level rise would look like on a daily basis. Returning to this graph, it helps to understand why it is very important for the community to know that sea level is rising, how fast it is rising, and for Southeast Florida as a whole to plan for sea level rise adaptation together. As an example, the walls and roads built in the 1960s were designed assuming water levels did not change. This assumption was incorrect, and now they're vulnerable to flooding. By having a unified sea level rise projection for the Southeast Florida region, the community can build smarter today, having an understanding of what sea level rise will be in the future, and hopefully avoiding flooding, damage, and that disruption I described before. One last note. Looking at the past helps us to understand that the rate of sea level rise changes over time and justifies the need for updating the region's future projection regularly. The Southeast Florida Regional Climate Change Compact updates the projection every 5 years. As greenhouse gas emissions increase, sea level rise will accelerate, and the community will need to plan for that acceleration. So here is the unified sea level rise projection. As you can see, it actually consists of 4 curves. We highlight the planning horizon of 20 years projected for year 2040, and also the 50-year infrastructure lifespan in 2070. So it's year 2020, So we assume 20 years from now is 2040 and 50 years is 2070. The 50-year lifespan of a structure. We know we have buildings that last longer than 50 years, but that's the generally accepted kind of definition of what the lifespan of certain pieces of infrastructure are. The projection starts in year 2000. This is a change from the previous projection. When I was describing mean sea level in the beginning, I noted that the tidal epoch will shift by 19-year periods. So this projection begins in 2000 because that is referenced to our most recent tidal epoch. It begins also with observed data from 1992 to 2017, and that's an average of over 5-year periods. So just like I described the black line in the first slide, it's averaged observed data over 5-year intervals. And I'll highlight that it includes the IPCC, so the Intergovernmental Panel on Climate Change median. It includes the NOAA regional projections, including the NOAA Intermediate High Curve and the NOAA High Curve. And then we also show the NOAA Extreme Curve. And although we're not suggesting that for design or planning specifically, it's important to display the bounds of potential sea level rise and for us to have a very real and active discussion about emissions and what potential sea level rise scenarios should be. So the blue shaded zone between the IPCC median and the NOAA Intermediate High Curves should be used for projects with life expectancy of less than 50 years. This is the time period that we have the most confidence of what sea level rise will be. The shaded zone between these two curves is generally recommended for projects that can be adapted over time, meaning that we could alter them as needed so that they could deal with a higher sea level rise scenario in the long term. Projects or pieces of infrastructure that are not interdependent with others, so meaning that if the structure does fail, it wouldn't cause cascading impacts to other pieces of infrastructure or other services that were connected to it. And then ultimately, you have to make a decision of whether the costs of the infrastructure in designing to the upper curve outweigh the potential losses of designing to a lower curve or a lower sea level rise scenario. The NOAA High Curve should be used for critical infrastructure projects that we do not want to see fail. And it also provides a useful estimate in the long term. I mentioned that we have high confidence in the near term, kind of between now and the next 50 years. And as we project out to 2120, we are not sure what greenhouse gas emissions will be by then. We do not know what how significantly we will reduce greenhouse gas emissions by then. And so we need to account for a higher sea level rise when we look out at the longer projected term. So this chart shows how the new projection aligns with observed data since the year 2000. The gray and black lines are based on measurements from the Key West tide gauge. The blue lines are the IPCC median and the NOAA Intermediate High projections. From 2000 to 2013, the trend in the observed data, the black line, follows the IPCC median. After 2013, the trend is between the two projections. And so in looking at this graph, we've essentially, the comparison validates the use of the projection. You can see that we are right on trend with the observed data. And actually the curves that have been selected as part of the projection are very well tracking with the observed data. Also, since the projection is based on mean sea level, it highlights that water levels will regularly be much higher than the mean sea level projections, depending on the tides and the weather. And so in that comment, I'm recognizing that the gray lines, the actual water level data, can be much higher or lower than the mean sea level projection itself. And so you need to account for those tides and storm surges and other weather events. So the Unified Sea Level Rise projection is essential for our policy and our planning and the adaptation projects that are underway. As an example, in Broward County and across the region, there's been evaluation of regional standards for coastal infrastructure, in particular seawalls. And so here's an example of how in Fort Lauderdale, the policy of requiring higher seawall heights has helped this community prevent flooding from getting onto the property. Also, the sea level rise projection is relevant to designing the actual finished floor elevations of buildings. The buildings need to be high enough that you're not getting flooding into that first floor, and you want to avoid that damage, and you want to design the surrounding infrastructure to make sure that it's usable even during flood conditions. And there's all sorts of projects that are dependent upon the Unified Sea Level Rise projection and that need to incorporate not only the data of the projection, but that there needs to be decisions made on whether we design to the NOAA intermediate high curve or another value. And so those are the types of projects and decisions we're going to discuss later in the webinar. But ultimately, it's essential for us to provide this protection for the community and to plan the upgrades that are necessary and to use the projection itself. So I'll just say that the scientific community's understanding of these processes continues to improve, and that's why we continue to update the projection. And there may still be some uncertainty in what future sea level rise will precisely be. However, we are in absolute agreement that the range of projections that's included in the Unified Sea Level Rise projection can easily be interpreted by policymakers and used in the design of climate adaptation. And we hope that we help provide the information in order for you to do that. And with that, I'll take any questions, Lauren.
Great, thank you so much, Sam. So the first question that we have is there a westward or horizontal equivalent of intrusion for each unit of vertical sea level rise? So I think this question is getting at the movement of groundwater inland.
Right, so it'll vary across each county, but in Broward County, I shared one image. So I showed the areas that were east of the salinity control structures. There was essentially a 1-to-1 response. For every foot of sea level rise, we were seeing a foot of groundwater table rise response. Then in that middle section, it starts to be only a half a foot response to a foot of ocean rise. And then further west, it even decreases from there. Is that helpful?
Yes, very good, thank you. Another question was, why does the sea level rise, the Unified Sea Level Rise projection, mix curves from different sources? So, i.e., why are we using IPCC? Why are we using NOAA?
Sure. So in our next two presentations, we are going to be describing the methodology and the reasoning for the selection of the curves, as well as Dr. Gassman will be presenting on how to apply the curves. And how each project you may decide to select different curves. But overall, the reason that you need the range is we have some uncertainty in sea level rise for the long term. As I just mentioned, we have high confidence in the short term, but there are still multiple sea level rise scenarios that could occur. And so depending on the project, depending on your cost of your project, the risk of the project failing, you may need to make a decision on what you invest in today and what kind of risk tolerance you can have in the future. And so it's not as simple as having one finite number.
Great. Another question was, what factors and assumptions make the projections exponential versus the linear historic numbers that we have had up until today?
Absolutely. So the next presentation will describe some of the regional effects that have been occurring. Part of it is a mathematical analysis. So NOAA actually provides data looking at a linear trend, and you can draw a straight line through the graph that I provided in the very beginning and get a certain linear trend, and it won't account for the recent accelerations that I described that are a response to some of the local, regional physical processes as well as global changes. And we're going to talk about that in just a second, so I don't want to give too much away. We'll pick it up. If we haven't answered the question thoroughly in the next presentation, we'll have a better discussion.
Great. Yeah, I think there's several questions that came in that might be answered later. So we're going to hold on them, and I'm actually going to move us into our next presentation. So thank you so much, Sam. This was super helpful introduction. Next, I'd like to turn it over to Dr. Robert Kopp, who will discuss the connection between future sea level and greenhouse gas emissions. Dr. Kopp is an esteemed climate scientist who serves at Rutgers University as the director of Rutgers Institute of Earth, Ocean and Atmospheric Sciences, and is a professor in the Department of Earth and Planetary Sciences. Dr. Kopp is an author of the 4th National Climate Assessment and the Intergovernmental Panel on Climate Change forthcoming 6th Assessment Report, and provided early counsel to the compact in its process to update the projection in 2019. Dr. Kopp, we are really grateful for your support and to have you with us today. Thanks for being here.
Thank you, Lauren. My pleasure. So in my 15 minutes, I'm going to dive into sort of the scientific underpinnings of sea level rise projections. So the next talk after mine is going to talk about the choices that were made in going from the underlying science to a specific scenarios for use. So I want to ground us all on sort of what we know at a scientific level about sea level change now. So why can't I? There we go. So I'm going to address at least 3 and possibly 4 questions, depending on how the time goes. So first, how are climate and sea level changing today? Second, what are the factors driving those sea level changes? And I know some of the questions that were raised in the Q&A were related to that. Third, what can we anticipate in the future? And if I have a little bit of time at the end, I'll talk about sort of what we do about it. But that's sort of, I think, coming out of this, and we'll skip that if need be. So to start with, how are climate and sea level changing today? Well, step out of the big picture. For over 800,000 years, carbon dioxide concentrations in the atmosphere stayed between about 180 parts per million during periods we call ice ages and 300 parts per million during periods we call warmer interglacials. And so you can see, actually you probably can't see because I can't move the pointer on the screen, but you see these ups and downs in the graphs. So if you look at this, say this spike today, that's an interglacial. If you look at the low point right before us, that's a glacial period, an ice age. There was a giant ice sheet sitting on top of New York City. In 1913, carbon dioxide concentrations surpassed 300 parts per million, reaching the highest levels of the last 800,000 years. In spring 2014, they surpassed 400 parts per million. And today we're at over 410 parts per million. If we zoom in on that a little closer, the last 250 some years, 1750, before the Industrial Revolution, carbon dioxide concentrations were around 277 parts per million, which we know from bubbles of gas trapped in ice cores. Over the next 100 years, they rose by about 10 parts per million to 287 parts per million. Over the next 50 years, they rose by another approximately 10 parts per million. Over the next 50 years, they rose by about 15 parts per million. That brings us to 1950, 311 parts per million. Between 1950 and 1988, which was the time of the first congressional hearings on climate change, carbon dioxide concentrations in the atmosphere rose of 40 parts per million to 350 parts per million. And as I said, today they're around 411 parts per million. So one important point to take away from this is that though we are living with the effects of all of the emissions that have happened since the start of the Industrial Revolution, most of them have happened since 1988. So this is really not a long legacy thing. This is the last 30 years. So to look at why those carbon dioxide concentrations are going up, well, the basic driver is the emissions of carbon dioxide from fossil fuels, which is responsible for about 90%, and land use change. This figure here is showing you cumulative fossil carbon dioxide emissions. So if we look at, say, 1750, we start at 0. So 1900, the numbers are showing you all of the emissions from 1750 through 1900. So Between 1750 and 1850, there were about 5 billion tons of carbon dioxide emission. Between 1750 and 1900, there were about 45 billion tons. And by reference, that 150 years of emissions is roughly the same as 1 year of emissions today. By 1950, we had got into 230 billion tons of cumulative emissions. And by 1988, to 750 billion tons of cumulative emissions. We're now at around 1,610 billion tons. So again, the majority of emissions have happened since 1988, since the time of the first congressional hearings on climate change. Okay. As a result of these emissions, our planet is running a fever. This figure here is showing you global average surface temperature, with 0 being the average in the end of the 19th century. Between 1980 and 2018, we've seen this rapid increase at a rate of about 0.3 of a degree Fahrenheit per decade, leading to a global average temperature in 2018 that was about 2 degrees Fahrenheit above the late 19th century average, and leading the last 5 years to be most likely the warmest 5 on record. Now, we're here to talk about sea level change. Since the early 1990s, scientists have measured changes in the height of the sea surface using satellite-borne radar. So that's allowed us to construct a global picture of what's happening to the surface of the sea. And you can see from maps like this is from the National Climate Assessment, showing you rates of change in sea surface height from 1993 to 2015, that the sea level is rising at different rates in different places. Indeed, over this 22-year period, there are even places like this area in the middle of the North Atlantic and these areas in the, you can't see my pointer, I'm sorry, but these areas in the middle of the North Atlantic, the areas in the Pacific, where there is even a sea surface fall. But if we look across the whole globe, the trend is clear. Global average sea level is rising, and it is rising at an accelerating rate. In the early 1990s, it was rising at about a rate of about 1 inch per decade in the global average. Today, it's rising at over 1.5 inches per decade. Now, is that unusual? Is that odd? Well, using statistical and physical models, we can piece together geological records and local tide gauge records from around the world to try to reconstruct how global average sea level changed over longer time periods. This photo here on the left is showing you a Rutgers team collecting geological samples that reflect sea level from a salt marsh in Newfoundland. Over here on the right, we're looking at a picture of the tide gauge in the Battery and at the southern tip of Manhattan. And when we piece together these sorts of records, we can construct a global average sea level curve that looks like this. So you can see there's this change in sea level over time. There's been some decline over this time period, and then it really starts consistently going upwards starting in the late 19th century. Has President Barack Obama tweeted when we first published this curve in 2016, we can say with a high degree of confidence, we're seeing the fastest rise in sea levels around the world in nearly 3,000 years. And since this paper came out in 2016, we can say that essentially we have complete confidence that the current century is rising faster than any time in at least 3,000 years. Now, this is having real effects, as was discussed earlier. So sea level is making, for instance, high tide flooding more common. In Miami Beach, according to NOAA, the number of high tide flooding days have increased by about a factor of 4 since the 1990s. So what's driving this sea level change? The single largest effect are changes in the amount of ice stored on land. Shrinking ice sheets at the poles and shrinking glaciers on mountaintops are responsible for a majority of the 3 inches of global average sea level rise that happened from 1993 to 2017. This is a picture of a cliff on the edge of the Greenland ice sheet at Jakobshavn in Greenland. And this is probably a cliff of about 60 meters, 100 feet high or so. And we get processes happening, particularly where ice sheets interact with the ocean, that can lead to fairly rapid loss of ice. Now, if we step back, look quantitatively, here's a breakdown of this land ice turn. So in Greenland, there's been about 1/2 inch contributed to global average sea level since 1993. And this is happening at a rate we can observe to be accelerating. This map is showing you, based on the changes in the Earth's gravitational field, the parts of the Greenland ice sheet that are losing mass in red, and the parts that are gaining mass because of enhanced snowfall in a wetter, warmer atmosphere in blue. In Antarctica, there's been contributions of about 0.3 of an inch since 1993, mostly concentrated in this dark red area known as Thwaites Glacier. But mountain glaciers spread around the world have actually been the single largest ice term, responsible for about 7/10 of an inch of sea level rise globally since 1993. And we're worried about these because the potential for sea level rise from land ice loss is much larger than just this about 1.5 inches that we've seen since 1993. If we do an inventory to say, okay, how much water is locked up in different land ice reservoirs, so that if you were to lose all of them, how much would sea level rise? Well, if you were to lose all of the mountain glaciers on the planet, we would see about 1 foot of global average sea level rise. If you were to lose all of the Greenland ice sheet, you would see about 23 feet of sea level rise. If you were to lose all of the West Antarctic ice sheet, we would be looking at about 16 feet of sea level rise. If we were to lose all the ice in East Antarctica, we'd be looking at about 171 feet of sea level rise. Now, this is just an inventory. We're not necessarily on a course to lose all of this, although we might be on a course with unchecked fossil fuel emissions. But even so, it would take millennia for all of this liquid ice to turn into water in the ocean. But when you're looking at such large masses of ice, such large potential amounts of sea level rise, we have to be very concerned about our ability to make small changes on them that can be quite significant from our perspective. So here's our budget. So we said about half of the 3 inches are due to ice melting. The next largest factor, about 40%, is due to changes in the density of the ocean. It expands as it takes up heat, just like water in a pot on the stove takes up heat. And finally, we have about 10% that is due to changes in the amount of water stored on land. So pumping groundwater, for instance, allows water to run off into the ocean, leading to changes in sea level. Now, that's the global average story. When we start looking at specific places, like in South Florida, the story becomes more complex, right? So from 1993 to 2017, out of about 4.7 inches total in Miami Beach, there's about 1.3 inches, as I told you can see my pointer, so I'm gonna continue using it. 1.3 inches due to the global uptake of heat. There's about 0.3 inches that are due to the land sinking as a result of natural processes. There's about 1.4 inches due to the melting of ice on land, a little bit less than the global average because of the way that moving large masses of ice around actually changes the Earth's gravitational field and changes where the water goes. And so that leaves about 1.7 inches, which are due primarily to changes in the interactions between the oceans and the atmosphere. So changes in winds and changes in currents. And some of those may be driven by climate change. Some of those may be natural oscillations. So what sea level rise can we anticipate in the future? Well, we need to look at all of those processes and to have a way of quantifying this. So we've developed a framework at Rutgers for doing this that's ended up being widely used, and I'm just going to quickly show it to you. So looking at changes in the height of the land, from that we can look at historical trends, and that works pretty well in places where that's largely a long-term natural process, as it is in Florida. For changes in groundwater withdrawal and dam construction, we can look at how changes in population have impacted the amount of water extracted and the amount of water stored on land. For changes in winds and currents, that's really where climate models do their best. And so we rely here upon the tools that use the same physics that are used to simulate the weather, but looking at longer timescales and looking at ocean as well as atmosphere dynamics. And these are sort of the core source of information for this ocean component. And then the really hard part is what's happening with the ice, particularly in the ice sheets. And so the way we deal with that is to look at various different ways of modeling how ice sheets and glaciers behave. Now, our open source framework with some modifications has been widely used in US stakeholder-driven assessments. So it underlies the projections in Washington State, Oregon, California, Maryland, Delaware, New Jersey, and was an important contributor to helping develop the scenarios in the fourth National Climate Assessment, which are one of the key inputs for the South Florida report. Now, a key driver of the range of possible futures is the range of possible human emissions. So this map here is showing you some different possible scenarios of future emissions. So in black, we're looking at global greenhouse gas emissions. And this is slightly larger than the numbers you may have seen before, because this is also including the effects of gases like methane. Now, if we were to go back 10 years and say, okay, well, what's our baseline? At that time, most people were projecting a continuation of that increase in emissions we saw here. And that would have led to warming, most likely in the range of about 4 to 5 degrees Celsius, or about 7 to 10 degrees Fahrenheit by the end of the century, relative to the late 19th century. Fortunately, we've had some policy advances. We've seen prices of things like wind and solar come down quickly. And most people would say we're now actually on track for something closer to 3 degrees Celsius of sea level rise. So more like 5 to 6 degrees Fahrenheit of global average warming. So more like 5 to 6 degrees Fahrenheit. And if all the countries of the world met their pledges that they have agreed to in the Paris Agreement, it would drag it down a little bit more. That's still quite a ways from the goals laid out in the Paris Agreement, which are to limit warming to well below 2 degrees Celsius, or well below 3.6 degrees Fahrenheit. An important point to keep in mind is that to stabilize a climate at any level of warming, net global greenhouse gas emissions have to drop to 0. So even if, even this world that's headed for 2.5 degrees Celsius, that's still a world of sustained warming thereafter. Another key driver of the range of projections is the incomplete and, as I mentioned, rapidly evolving scientific understanding of how ice sheets and the oceans interact. Different ice sheet treatments give similar global projections through the year 2050. So here I'm going to show you 3 different ways of treating the ice sheets. I don't have time to get into the details, but we're going to look at 2050, we're going to look at 2100 for a high emission scenario, and we're going to look at 2100 for a low emission scenario. So regardless of what approach we use, we are looking at basically a likely sea level rise of about 0.5 foot to 1.5 feet, a global average between 2000 and 2050. Under a low emission scenario, one consistent with those ambitious Paris Agreement goals of limiting warming to 2 degrees C, we're looking at a global average sea level rise, regardless of the approach we take to the ice sheets, of about 1 to 3 feet. But when we start getting into the higher emissions world, here we're looking at a broader range. If we use a relatively conservative treatment of the ice sheets, similar to that the IPCC has used in the past, that might tell us we're just looking at a likely range of about 2 to 3.3 feet of sea level rise. But if we're taking some models that are incorporating physical processes the IPCC didn't consider in its last assessment report, that gets us to global average numbers more in the range of 3.7 to 7 feet of sea level rise. And a recent structured expert judgment study we used that sort of combines different lines of elements would have put that more in the range of 3 to 6 feet. So I'm going to skip over what we do about sea level rise. You'll hear more about that, but I guess we're running out of time. Just to say there's an adaptation element that we have to consider, but however we choose to adapt, the starting point is and has to be climate change mitigation. So this is showing you global greenhouse gas emissions, same thing I showed before, but now zooming in on the next decade. So here's where we are with current policies, a slight increase. To be on a world consistent with a 2 degrees C warming, we are looking at close to a 30% decrease in global greenhouse gas emissions over the next decade. Now, regardless of emissions, we're looking at likely global average sea level rise of about 0.5 foot to 1.5 feet between 2000 and 2050. Under current emissions, we're looking at likely about 2 to 5 feet by 2100 and a high-end number closer to 6 feet. And under low emissions, we're looking at a likely range of about 1 to 3 feet, and the high-end number would be closer to 4 feet. So thank you. Sorry for running slightly over, but I think we have 3 minutes left for questions.
No, that's fantastic, Dr. Kopp. Thank you so much. And we did have some questions come in during your presentation, which was extremely informative. One question that we had was whether the ice melt that is occurring that you spoke of is happening at a rate that is simultaneously dampening heat expansion within the oceans.
So the broad answer is it's having some effects that don't show up when you look at, say, global average thermal expansion, but it is affecting ocean circulation around the Greenland ice sheet and around the Antarctic ice sheet. And so, the effect of that go in these things that those complexities of ocean ice sheet interactions that need more research. But broadly, sea level ice sheet melt in the North Atlantic off of Greenland likely leads to a slowdown of the Gulf Stream and potentially an increase in sea level rise locally in North America. Ice sheet melt in Antarctica may have a bit of a dampening effect on the ice sheet melt rate because of the way it affects the regional climate and sea ice. But that's really sort of cutting edge science, how those interact.
Fantastic, thank you. What are the critical thresholds or sort of canaries in the coal mine, if you will, that the scientific community is tracking to determine whether the IPCC median and the NOAA intermediate high are no longer the most likely future scenarios or predictions?
Yeah, so again, I think that has to do a lot with the ice sheets. And so I think we're going to learn a lot over the next few years through intensive study of places like Thwaites Glacier in the Antarctica. But the negative thing is some of the processes that we're most concerned about kicking in, things like the development of unstable ice cliffs, are things that we're probably not going to see until the second half of this century. So the range of projections is relatively narrow through about 2050. And then the breadth comes from those high emission scenarios later in the century and beyond. And I think we need to get a better understanding of how ice sheets work when we push them so far outside the climates they've experienced over the last several hundred thousand years. You're on mute, Lauren.
Thank you. So we certainly know that these two things interact, but a question was, are there models that include and quantify consumer behavior change? How much is the rate of sea level rise entirely dependent on policy?
Okay, this is getting into the realm of climate economic models, and I'm a consumer rather than a developer of those myself. But I should say that you're unlikely to see, say, a 30% reduction in global greenhouse gas emissions over the next 10 years from consumer behavior. That is really a policy issue. We're dealing with areas where common action is sort of necessary to reach the scale that you need of global impact. And so, you know, the single most important action you can take as an individual is participating as a citizen.
Right, of course. So someone is curious, if we were able to meet the 1.5 degree lowest emission pathway or scenario, can you talk a little bit about what that would mean in terms of future sea level rise? Yeah,
so I would just say that at one point, the differences between emission scenarios show up slowly because ice sheets are really large and oceans are really large. So ice sheets, you know, to raise sea level by an inch from melting an ice sheet requires melting about 1 trillion tons of ice. So we should just keep that in mind as context. The differences in terms of sea level rise between a 1.5 degree C world and a 2 degree C world are probably not going to be very large in this century. We're probably talking about a few inches. The substantive difference is that we know there are points at which the ice sheets become less stable and we see a more rapid loss of ice with warming, and we don't know where those are, right? So, you know, there are models that suggest that maybe, you know, there's a threshold in the Antarctic ice sheet somewhere between 2 to 3 degrees Celsius, but figuring out exactly where those are is hard to determine. So, and they'd say the basic thing is the less you warm the planet, the less likely you are to cross one of those thresholds. And that's really where the largest effect of a 1.5 to 2 degree C world is going to show up, is that where, you know, we have this risk, we aren't very good at quantifying it right now, but we know it's less the less warming we have.
And I'm just gonna, we have time for one more question. We have a lot more questions coming in, and I apologize, we're not gonna get to all of them, but I think this one's really interesting and timely. Is, do you have any thoughts on really how long we would need to sustain the current reductions in emissions that we're seeing due to the downturn of economic activity driven by the global pandemic for it to have any real long-term effect on emissions in the long run and subsequently sea level rise?
Yeah, so a couple of points to make on that. So one, where you put the endpoint of your question is going to matter, right? If you look at some of the projections of emissions changes in May, not surprisingly, there was a large uptick in emissions in May relative to March and April. So these very large numbers people were quoting in April, right, were sort of assumed that the trends seen in March and April continued over the course of the year. The second point is that what matters is cumulative emissions, right? So putting more carbon dioxide into the atmosphere, right? What matters is that total pool of emissions. So, you know, a 5% drop, let's probably a high end of what might happen this year. It matters not very much if then we go back to trend below. So to get on, say, that path that shows you of limiting warming to 2 degrees Celsius, right? You need to have something of comparable scale to that sort of a 5% drop, maybe slightly smaller for 2 degrees, a little bit more for 1.5 degrees C every year until we get to net zero emissions effectively. Now, the worst possible way of reducing emissions is shutting down parts of the economy. That's sort of like, if you want to, yes, you can reduce emissions, but you do it in a way that sort of causes the most pain and when in fact you can, in many cases, be reducing emissions in the way so it doesn't cause pain at all, that causes net economic harm, benefit. So the scale is comparable to what we've seen from COVID, but it's not at all, the experience should not at all be the same, right? We want to be decarbonizing by transitioning the economy, not by shutting down the economy.
Absolutely. Absolutely. I think that's a really key point. We need to find opportunities, and there are certainly opportunities to both decarbonize and ensure continued economic prosperity and stability. So Dr. Kopp, thank you so much. This was a wonderful presentation. I think we all took home the message that, the opportunity for action on mitigation is really now, and what we do today is going to have major consequences for the rates of sea level rise in Southeast Florida into the future. So thanks for being with us. With that, I'm going to turn it over to our next presentation, which is really on the technical overview and methodology of the 2019 projection, presented jointly by Dr. Samantha Danchuk, who you heard in the first session, and Dr. Jayantha Obisekera. It is a pleasure to introduce Dr. Obisekera, who is a research professor and director of the Sea Level Solutions Center at the Florida International University. Dr. Obisekera served as a member of the Federal Advisory Committee, which directed the development of the National Climate Assessment in 2014, and he's also chaired the Climate Compact's Technical Advisory Work Group in updating the 2019 sea level rise projection and drafting the projection guidance report. Dr. Obisekera, we are so appreciative of your time and leadership and expertise. Thanks for being with us.
Thank you, Lauren. I assume you can all hear me?
Yes, we can hear you.
Okay. So it's always hard to follow Dr. Kopp, who is really an expert. We are very, we're very pleased to have him, starting from the beginning. So I'm with the Florida International University, part of the Institute of Environment, which includes both coastlines, oceans, freshwater resources, and land and biodiversity. And I'm also part of the Florida Climate Institute as a co-director. So it's also a contribution from the Florida Climate Institute to the Southeast Climate Compact. So what I want to do is, starting from the excellent presentation from Dr. Kopp setting the stage, I want to go through why we selected the curves for the 2019 projection. And I'm going to share this presentation on the methodology and technical overview with Dr. Samantha Danchuk. She will follow me on this. So let me go ahead and identify, let me see. Okay. Why is it not moving?
You click your mouse or use the advanced arrows on your keyboard.
Okay, now it's moving. Can you go back one? Okay. Yeah, so I want to recognize all the folks who were in our work group. As I think Lauren and Sam mentioned earlier, a broad cross-section from agencies and universities and nonprofits. But I also want to recognize all the experts that we consulted, including Dr. Cobb, who was very helpful with us. Some of the data and some of the work we have used actually came from the NOAA 2017 report that Dr. Kopp mentioned, and some of the methods that were used in that National Climate Assessment report. So I want to recognize their contributions. So let's start with the, what's happening near to us. I think Sam mentioned these sea level, historical data on sea level. Unfortunately, we only have like 4 tide gauges in our area, which has some decent length of records. The longest being the Key West, which is one of the best tide gauges around the country. And then we have a couple of other places, Miami Beach or Virginia Key, and then the Lake Worth, which has a sporadic. And the basic point here is that they have all been rising almost at a linear rate up to now, in the range of about 9 to 14 inches. And I think the expectation, for the reasons that Dr. Kopp mentioned and we discussed earlier, the acceleration is already happening at some level, but it's expected to increase further. So I wanted to focus on the more recent period, and I'm seeing something that's very interesting. Since about 2012, we almost have had a step jump. You can see these little windows for each of the each of the tide gauges. You can see almost a jump in the sea level, and which is interesting. I have seen the same phenomenon with some of the water control structures managed by the Saltwater Water Management District. So it's almost like a rapid rise in the rate of sea level rise, and almost like a shift. Now, the question is that a persistent change that we will expect in the future? Or is that like an episodic event that may have happened in the past? But as you can see in the Key West tide gauge, you have had similar periods, but now, since these rapid rises are happening at a higher sea level, the impacts are greater. So this is of concern. And there have been some theories on this increasing temperature, changes in the Gulf Stream, and others. So, it's probably too early to attribute that definitely it's some factor, but it's something we're already observing. And we are seeing nuisance flooding and other implications of that in the region. I think Dr. Danchuk showed some graphic like this for the historical data. What I want to point out is that in the recent rise since about 2000, about 40% of the entire amount, 10.7 inches, happened in that most recent period, that rapid jump. But so this is something we need to keep in mind when we project the sea level into the future. The other take-home point in here, which Sam talked about, is the tidal epoch. And typically, because sea level is rising, NOAA changes the tidal epoch. It is the approximately 19-year period, which is currently 83 to 2001, through time, because there's no point in measuring sea level with respect to a datum going back a decade. So this tidal epoch is going to change in the future. And so that's an important aspect for us in using the sea level curves. And the other aspect is we use the midpoint of that tidal epoch as the anchor point. We used that in the 2011 projections, but now we have this data from projections data from year 2000, which is going to be our new anchor point. And I will explain the reason for that later, but that's something we need to keep in mind. There has been about 0.2 inches increase in that mean sea level datum from 92 to 2000. So, and by the way, I'm going to be mixing up metrics and English unit, and I apologize for that because some of the global and national level data come in metrics unit. And if you you don't remember your conversion factors, 1 meter is about 39 inches or about 3.3 feet. 1 inch is about 25 millimeters. So moving on, so I'm going to rehash some of the things I think Dr. Cobb mentioned. I want to explain why we should be concerned about the factors affecting regional sea level, starting from the global level, because what we are interested in is what is to be expected next to South Florida region. So at the global level, there are two primary ways that the global mean sea level will increase. It's like a bathtub. You have one thing that Dr. Cobb mentioned, thermal expansion. When you increase when you have, say up to now, about 90% of the heat is in the ocean, that expands water, that's a thermal expansion. And then the other one is like in a bathtub, you add or basically stop water going into the ocean, like in the case of groundwater withdrawal or building dams and others. But one of the, so the two, several sources of that water going into the ocean, one is the glaciers that I think Dr. Cobb mentioned, or the water coming from the land surface, what we call land water storage. But the big unknown is this ice sheets, polar ice sheets, Greenland and Antarctica. These ice sheets, so it's very important to project what we are going to expect from those. And that's the source of big uncertainty that I will talk about later. So this is an interesting graphic to show how the ice sheets have been melting. And you see on the upper right-hand corner, a very cool technology in terms of measuring the gravitational field around the Earth using a pair of satellites known as GRACE satellites. And by measuring the distance between those satellites, they could measure small differences in the gravity. And that has been used to estimate the ice losses from the polar ice sheets. As you can see, those graphics show, continuing declining of ice sheets. Greenland has had about 125 gigatons per year, and Greenland had about 200 some gigatons per year, and Antarctica has had about 125. So you need about 360 gigatons to make a change in about 1 millimeter sea level, and that's the amount of water that would take. So as you can see on the lower left-hand one, the contributions from the Greenland has been larger than the Antarctica, and then the thermal expansion has been the largest up to now, up to about 2015. But the question is, what is to be expected in the future, and how well can we predict those? I just want to, show this graphic to show that there is enough technology and measurements and estimations that you can do what is known as a sea level budget. Basically, can we add the thermal expansion and glacier contributions and ice sheets and compare that with the observations coming from the tide gauges? And you can see from these graphics, fairly good match in terms of what is observed from the water levels and in tide gauges and satellites with contribution. So we have a better idea of what the contribution has been up to now. So the other important aspect for us near South Florida or anywhere around the world is what other factors affect the regional sea level. And some of the modeling that Dr. Cobb mentioned at Rutgers, they account for all these three factors. One, obviously, the ocean circulation is like the Gulf Stream next to us. Is there a persistent change in the ocean circulation pattern next to us that would affect our regional sea level? And the other more important effect is the ice melt effect, changing the gravitational field. And I'll come back to that in the next slide. And then obviously we have the vertical land movement due to various sources, particularly the subsidence, or even in places like Alaska, it's an uplift due to tectonic activity. So when you measure the sea level with respect to the land nearby, you really need to account for the vertical land movement as well. So these three factors need to be accounted for. And this looks complicated, but it's really not that. But in the modeling that Dr. Cobb mentioned, you have the global mean sea level, due to those three factors I mentioned. Then there are two other sources of changes, what we call climatic or non-climatic. Climatic, I'll go into this in a minute. In terms of global mean sea level, I mentioned either we add the water due to ice sheet melting or land water contributions. Then the two parts of the climatic processes are, one is the thermal expansion and salinity driven circulation patterns. And the other one is the one that I mentioned, the gravitational field changes. And basically, this is an interesting phenomenon that people don't talk about a lot. So when you take off large amounts of ice from places like Antarctic ice sheet and Greenland, the gravitational pull they had on the water next to it is basically reduces. Basically, so the sea surface basically bounce back in other places, right? Maybe dropping right next to the ice sheet. So this change in gravitational field and even in some cases Earth rotation could have implications for regional sea level throughout the globe. And the other aspect we have to account for is what non-climatic changes due to compaction, subsidence. But one other aspect is called GIA, or glacial isostatic adjustment. Is basically, Dr. Cobb mentioned these thick ice sheets that were there thousands of years ago. And when they came out, the Earth mantle still rebounds, and that needs to be accounted for accurate projection of sea level change around the globe. So as a part of this committee, we went through all the reports that are around. There were several national reports, and we zoomed in on this one report that no National Climate Assessment News, published by NOAA in 2017. I was privileged to be involved in the first three national level in some form or the other. And then we also looked at the last year's special report on oceans and cryosphere. And then we also looked at regional projection. Many counties, cities have produced regional sea level projections, and we kind of looked at those to understand how they develop their curves, so, including the New York one. And I think they were very useful. So now, more recently, due to the reasons that Dr. Cobb mentioned, we have limited understanding of certain aspects of sea level rise. And there are two primary sources that I have identified here. One is the greenhouse gas emission pathways, basically to what pathway we would follow in the future. Are we going to be reducing the greenhouse gases, or are we going to be following the business as usual? And these numbers or names called representative concentration pathways are basically those future greenhouse gas pathways that the world might follow. And unfortunately, the data shows that we might be following this RCP 8.5. But I think there have been some policy changes. We may have some hope, but for planning purposes, and I will emphasize this later, we assume that RCP 8.5 is a reasonable planning scenario, or at least give more weight to that. The other aspect contributing to what we call deep uncertainty is the lack of understanding of the marine ice sheet dynamics. I know there are several ways, and I think those are not understood or represented well in the ice sheet models. And I think that is also contributing to this deep uncertainty. Just to comment on this topic of deep uncertainty, we know how to handle uncertainty, but deep uncertainty is when your models don't agree or experts don't agree, and you tend to use more like a scenario approach in some cases, but informed by the science. And I want to point out there is a webinar on the during the third one on how to deal with this deep uncertainty using a approach called dynamic adaptive policy pathway that we have scheduled. So I will try very briefly to what was done in NOAA 2017 by the team of Dr. Kopp and others. And he mentioned the use of various methods for ice sheet mass changes that is informed by the climate models, but more importantly, expert elicitation, because the climate model may not be perfect. And also we use what are known as fingerprints. Basically, how does that ice melt distribute throughout the globe, and those are called fingerprints. And then glacial mass changes and oceanographic processes used in the model. So a variety of models were used in that methodology to simulate potential future sea level rise realizations. So various greenhouse gas pathways, as you could see, RCP 2.6, 4.5, and 8.5. And then based on those, in that study, in that work, several scenarios were developed, and I will mention those in a minute. So the idea is that can we use what are known as conditional probabilities, or use these greenhouse gas scenarios, conditioning the future sea level, and pool them into one group to see how many scenarios can be used and what are those projections. And I will, we use this data extensively. And one advantage of this data set in the NOAA 2017 was that, as opposed to the previous projections, we actually had regional projections near Florida, and those were produced by the team that Dr. Kopp was involved. A gridded data sets all around the United States and also at tide gauges. So we were able to pick the regional projections, accounting for all those factors I mentioned. So looking at these 5 scenarios, actually 6 scenarios that are shown here, we opted as a work group to focus more on the high scenarios, the NOAA high scenario and NOAA intermediate scenario. And Sam mentioned the NOAA extreme scenario. We are not recommending that for planning purposes. That is a catastrophic ice melt scenario. For information only, we provided to indicate what could happen in the future, but not necessary for planning purposes. So the NOAA high, NOAA intermediate were picked from 2017. So we could have picked the NOAA intermediate scenario, that's the blue curve here. But to be consistent with the previous projections, we actually opted to use what we call IPCC median. And many don't understand what that means, but basically that was a 0.73 meters by 2100 at the global level. We sort of interpolated the other curves for corresponding to that IPCC median value, primarily to be consistent with the previous projections and so that we have some consistency. But the rest of the curves were primarily from 2017. Now, there was a lot of questions on the probabilities, and this is an area of intense discussions in the community. And this table came from the NOAA 2017 report. And basically, for a given scenario, depending on your greenhouse gas pathway, you can have a higher and higher probabilities. For example, if you pick a low scenario, and if the world follows RCP 8.5, you are definitely guaranteed to exceed that low scenario. As compared to a higher scenario, you may have a lower and lower probability, even with that higher greenhouse gas scenario 8.5. So this is useful in some ways to determine your chance of a particular scenario, but we really didn't use that probability to make decisions. We basically recommended some, the 3 scenarios or 4 scenarios you are seeing: extreme, NOAA extreme, NOAA high, NOAA intermediate high, and NOAA IPCC median. So why we focus on RCP 8.5? I have quoted here a couple of items from other reports that I mentioned. And basically, in the absence of, intense green adaptation efforts, it looks like, we'll have very high risk of coastal impacts due to rising sea levels. And those are more and more likely if you're following the RCP 8.5. And so we kind of assume that we are going to use that scenarios as a guide to give more weight to those higher scenarios that I showed you earlier. And then when we look at our sort of neighbor Tampa Bay team, they also recommended the use of RCP 8.5 for their planning in their region. So it seems like until we see more intense adaptation or mitigation efforts for planning purposes, we assume to give more, we assume to favor scenarios that are more consistent with either RCP 8.5 or even a little bit lower. And just to compare what they mean, and this is coming from the National Climate Assessment Report, intermediate high, has a it's in the very likely range under RCP 8.5. High scenario is also very likely in the very likely range under RCP 8.5. An extreme scenario is what is physically possible, sort of a worst case scenario of catastrophic ice melt. But we did not recommend that be used for planning purposes. So I'm getting to the end here. So what does that mean? We have the global scenarios. Fortunately, we have the regional scenarios, and it's in the form of a spreadsheet. Anybody can download from the NOAA website. And so I looked at all the grid points around South Florida and the tide gauges, and I plotted those together. And you can see the global curve is here in the black, and all the other regional curves, which account for those other factors I mentioned, oceanographic processes, gravitational effects, and vertical land movement, or non-climatic sources. They're all tied together. So we felt like using the Key West as a regional curve is helpful, is appropriate. I think we saw this earlier, and I will hand this over to Sam at this point to continue these discussions of the methodology.
Thank you, Obi. So I just want to share a couple quick points before we go to questions. And also share some data that's from the actual guidance document. And the guidance document is already posted online. Okay, so one of the questions we get is, in previous projections, we had used the US Army Corps of Engineers curves, low, intermediate, and high. These curves were not updated in the same time frame as the NOAA curves, which we ended up using. But I just want to show this data because this is actually a plot from the Army Corps Sea Level Tracker tool, and it shows the three scenarios in blue, green, and red, low, medium, and high. And then it also shows the observed data, which is the dark, thick line and the light blue line. And what you can see here is that the recent acceleration that's been described by Dr. Kopp and Dr. Obi-Sakara, really by the end, by 2015 and actually after 2013, we're at the actual red, the US Army Corps of Engineers, the high curve. So the observed data is already tracking with the high curve. So how would we be able to project beyond that point if we expect some additional acceleration over time? And so that further justified us using the NOAA 2017 curves that were projected regionally for Southeast Florida. Another question. That we get is, where does the unified sea level rise projection for Southeast Florida kind of sit within the range of sea level rise scenarios projected by NOAA and the Corps? And so I've tried to just point to where our curves are within the context of the other projections for Key West. And so you can see, the IPCC median obviously fits well within kind of the median scenario, the 50% scenario, the likely scenario of what sea level rise will be. Dr. Obi-Sakara already explained that we're tracking along the RCP 8.5 emissions pathway. And so the lower Army Corps scenarios, the low scenario and even the intermediate scenario are not likely And so we felt that we needed to provide projections that would be useful for the future. And so I'll just point out that even the NOAA high curve, you can see is not the highest curve that is available, and the NOAA extreme curve is included in the projection for kind of context, so that people can appreciate what the range of sea level rise scenarios are and what the worst case would be. Next. We also received many requests, and I personally wanted to see this in the most recent guidance document, and that was the Unified Sea Level Rise Projection provided reference to the North American Vertical Datum, or NAVD, elevation datum. So this is useful for engineering purposes and surveying and designing, and often you'll hear us say that the elevation or the finished floor elevation was built at 5 feet NAVD. So areas within our region are at 0, or even some are slightly below 0 NAVD. And so those areas will already see flooding as early as, you can see, 2040, because sea level rise will be at 0 to 0.6 feet NAVD. And then by 2070, we're reaching sea level elevations of 0.9 feet NAVD, upwards to 2.5 feet NAVD. And then for critical infrastructure, we're suggesting designing to 3.7 feet NAVD by 2070. And so just to acknowledge there that our low-lying areas within Broward County and within the other counties are at less than 2. And so by 2.5, a lot of those areas will be inundated. And then moving further up north along the county into the coastal ridge areas, our land elevations reach 5 and 6 feet NAVD, and in Palm Beach County, they're even much higher than that, especially along the dunes and the coastal ridge. So this is helpful because it gives you a fixed elevation to reference these numbers to. Although knowing what sea level rise will be in the future is extremely important, sometimes it's important to know what the actual fixed elevation of the sea level will be so that you can reference that to existing building plans. Next. Let's see if I have control again. So go ahead and just click through the animations on this. Thank you. So it's critical to notice what elevation datum from a projection is referenced to. Sea level changes every second. There's fixed reference points are necessary so that builders and surveyors and others have a common understanding of how high something is off the ground. The elevation datum used in the region, by Broward County and some of our other partners, is most often the North American Vertical Datum of 1988. I only stuttered there because Miami-Dade actually does reference to NGVD, which was the previously established datum. So I just wanted to click through in this animation to kind of show the usefulness of referencing to different elevations of interest. So mean sea level, as I noted before, is the local mid-tide for a certain time period. It's a lot easier to tell a builder to build to, minus 0.8 feet of NAVD, a fixed elevation, rather than asking him to know what, the midpoint between the high tide and low tide is, so that he can get reference to sea level, mean sea level, and, ask him to know what mean sea level rise was, or mean sea level was in 2000, or a different tidal epoch. It starts to get a little confusing. Sorry, I will just note that the mean high water represents the high tide, which is almost 1.5 feet higher than the mean sea level. The mean low water represents the low tide, which is about a foot lower than mean sea level. And mid tide today is approximately minus 0.5 feet NAVD. So in 2070, according to the NOAA intermediate high projection of 40 inches above the 2000 mean sea level, mid tide will be at about 2.5 feet NAVD. And so sea level rise can be referenced from mean low water, mean sea level, mean high water, or NAVD 88, whatever you prefer. But just note that the difference between these datums is significant, and it's very important to always understand what reference point you're using to clearly understand what the different water levels will be into the future. And to remember that our baseline is starting at 2000, because previous projections use different years, and we may use different years in the future. So really always important to focus on those details. So this next figure is just to confirm for you that, you know, we have been seeing higher high tides in the fall. We see the lowest high tides in the winter. Next slide. And as a result, we see nuisance flooding, or the king tides, or the disruptive flooding that is driven by sea level rise in the fall. And that is, you can see the purple lines here are the frequency of the nuisance flooding events. And you can see they're occurring more frequently since the data started being collected in 2000. And also I want to highlight that in recent years, there's even nuisance flooding that's occurring outside of the fall season. And so here you see a purple line in March, but we're noting that king tides or nuisance flooding events are happening, especially in May, and so other parts of the season. And so as we start to, next slide, migrate to a condition where we're reaching full inundation in those low-lying areas, you're going to see nuisance flooding events happen during the other parts of the year, happen more frequently. And so this figure actually is a projection of how, as sea level rise occurs, nuisance flooding will be more frequent. And so by 2030, we've got maybe 15 days of nuisance flooding, but by 2070, those low-lying areas that I showed you were less than maybe 2.5 feet NAVD, especially are getting inundated year-round. And so we need to plan for that, and that is one more valuable data set that is within the guidance document. And with that, I'll conclude.
Great, thank you, Sam. And if we can also bring Obi back in so we can do a few minutes of question and answer. We did have a number of questions come through during both of your presentations. One is, what is the effect of sea level rise on the freshwater/saltwater interface? And specifically, if you can kind of speak to the kind of infrastructure provisions that are being considered or advanced to protect our supply of potable water in the region. And I'll let you guys decide who's the most appropriate person to take the question.
I'll cover part of it, and you know, is that okay?
Yes, please.
Yeah. So there are multiple ways that the sea level rise will impact freshwater aquifers. You know, one is I think Sam showed the saltwater intrusion. Basically, the saltwater front will move inland. Concern is that future sea level will accelerate that saltwater front getting to the freshwater wells that are already there. They have been there for decades. So there are already some wells which are impacted by saltwater intrusion. The other issue is, as the sea level is rising, the groundwater table will also come up. And in South Florida, the space between your ground surface and the water table is like the sponge that would absorb the rainwater. So as the water table is coming up, that the storage capacity of that sponge is decreasing. That means you could have more flooding in the future. And in terms of infrastructure, you know, Water Management District already has a level of service program for flood protection. They're trying to revisit the water control structures and how to retrofit them or redesign them, accounting for future sea level and the groundwater table rise. I don't know, Sam, if you want to talk about the water supply issue or any other.
I'll just highlight, so the Compact website itself has case studies and can connect you to all of the work that's been done in the South Florida region related to this topic. It'll be really helpful because there's a lot to share. And I think webinar 3, there's a presentation related to the use of this unified sea level rise projection and groundwater supply, right?
Yeah, actually the next webinar will cover some of that, but great, thank you. So Obi, you talked a little bit about uncertainty around marine ice sheet dynamics, and at last year's annual Climate Leadership Summit in Key West, hosted by the Compact, we heard a presentation about the loss of permafrost in the northern latitudes and the contribution to sea level rise and accelerating CO2 release as that decomposition occurs. So the question specifically is, does the modeling and the projections accommodate about
I think the
permafrost loss?
Yeah, let me answer it this way. I remember the excellent presentation by Permafrost. And in our team, there were some members who actually gave some presentation and included a section on permafrost in the guidance document. The way the IPCC also considers that, but in my mind, it will impact the greenhouse gas scenario pathways. And it's probably more likely if that is going to play a significant role in future, we'll have RCP 8.5 like scenarios into the future, and that would increase the warming, and perhaps indirectly it will also affect the sea level rise. So it is accounted for, but it could be a very important source of greenhouse gases in the future if the permafrost is released from those areas.
Thanks, Obi. So a question from maybe outside of our region. For this update, there is, regional data that is comprising the projections. We're not just using global projections. The question is, how far in Florida geographically would these regional projections be appropriate and relevant? For example, in Martin County, this particular person says they're using the compact's projections for their vulnerability assessment, but they're curious if the projections would be applicable moving further away from South Florida, such as Brevard or Duval counties or even Gulf counties. Should communities be moving towards local projections that account for their own regional effects specifically?
Yes, I think that's a good question. We looked at the South Florida region, but as I mentioned before, NOAA 2017 report has a spreadsheet that has all the tide gauges all around the continental United States, and also a gridded 1 degree gridded product. So they can basically go to that spreadsheet and pick the regional projections near their areas and plot the regional curves. They may or may not be significantly different from the curves we have for Key West. But more important thing is, it will be nice if throughout Florida we can be consistent with the methodology. If you all use the 2017 projections, or we don't have to use the same numbers, we could go to the regionally relevant data sets from that data source.
So I'll just add, even across our Southeast Florida region, we're seeing as much as a half a foot of difference, in our tides from the north to the south. So moving forward even further north, it probably would make sense to reference a local tide gauge.
Very helpful. Great. Well, we certainly have a lot more questions, and I regret that we can't get to many more of them and stay on our schedule. But thank you so much, Dr. Obi-Janchuk, for all of your work on the projection and your presentations today. With that, I'm going to move forward and introduce our next speaker, who's going to close out our webinar for today, Dr. Nancy Gassman, who's going to help us better understand how to use the projection curves in our work. Dr. Gassman is the Assistant Public Works Director for Sustainability with the City of Fort Lauderdale. Dr. Gassman has also been a critical participant in the Compact's Technical Advisory Work Group to update several of its regional projections. So thank you very much, Dr. Gassman, for sharing your expertise and supporting the Compact over all these years.
Thank you, Lauren. With the guidance that has been provided so far, we've heard about why sea level rise is important, how the science is impacting our decision making. Obi explained how local factors were taken into account when we decided on those curves, and now we're at a point of, well, now that we have the projections, how do we use them? And so one of the valuable aspects of the Unified Sea Level Rise projection is that the document contains a lot of information to guide you on how to use the projection. And as Lauren had mentioned previously, on June 25th at 10 a.m., there will be an entire dedicated webinar from the compact to talk exclusively about applying the projection. And I'm just going to give you some highlights of the information that's already in the document so that you can start understanding how to apply and use the guidance that's available there. So I'm not able to advance the slides. Thank you. So the topics that I'll be covering today include how does the previous version compare to the current version of the projection? How do you select a curve depending on what you're working on? How to choose a reference elevation? And then where are there tools that are already out there and available to help understand how to get more detailed information about the actual numbers in the curves and visualizing sea level rise. Next slide, please. So the first question is, how do these two different projections compare? Next slide. So the previous version from 2015 used a 1992 baseline, and the projection for 2019 uses a 2000 baseline. And Sam explained the reason for that due to the tidal epoch. Well, when you compare the two, and there's a slight typo here, what you find is that the mean sea level in 1992 compared to 2000 is a little less than 1 inch. So that 1 inch is the difference in the baseline. When you compare the projections for 2015 versus 2019, the lowest curve increases about 2 to 3 inches for the 2030 planning horizon and 7 to 22 inches after 2060. And this goes back to something that Dr. Kopp said, how the curves currently stay fairly tight until you get about to 2050, and then they start to diverge. And there's a very helpful table within the document that shows how these different numbers compare across the different aspects of the different curves that were used for both the 2015 and the 2019 curves. So the question becomes, all right, which curve do I use when I'm considering either siting or the design of different infrastructure projects? So in making those decisions, what you're really looking at is the intersection between your planning horizon, whether it be short or long, over a 20-year time frame or over a 100-year time frame, and your risk tolerance within the infrastructure that you're building and the adaptability of that infrastructure. So if you're looking at a very short-term piece of infrastructure that is extremely critical, you might choose a slightly higher curve. If you are looking at a piece of infrastructure that is very long-lived, but not particularly critical, you have a little more flexibility on whether you choose a high risk or a high risk tolerance version or a low risk tolerance version. And I'll get into that a little bit more in a minute. So if you choose the IPC medium curve, and Dr. Danchuk showed how current sea level rise is currently tracking within the blue area, the blue shaded area of the 2019 curve, you would choose the values along the IPCC medium curve, that bottom curve, which is the lower range of the likely sea level rise, if that infrastructure had a fairly short lifespan, it was fairly adaptable, it could be moved, and it didn't have a lot of interdependencies with other types of infrastructure. And the consequences would not be particularly significant if it failed. And so there's 3 examples on the top of that slide. The first one being a stormwater culvert, the second one being a sidewalk, and the third one being a bus stop. Any of those would be fairly short-lived, 20 to 30 years, and your ability to move them would be easy, and there isn't a lot of other infrastructure that would be impacted if that particular piece of infrastructure failed. Next slide, please. The NOAA intermediate high curve, which is the top range of our blue shaded area, is in the mid-range of likely sea level rise. This would be the upper range of what you might choose if you were planning for important infrastructure that had up to a 50-year design life scale. And these would be projects that need a greater safety factor because there are greater interdependencies and they might be less adaptable. And the three examples that are on the top of the slide there is communication type infrastructure, or evacuation routes, or certain types of energy infrastructure. Those would be good examples where you would want to use the NOAA intermediate high curve in the compact's projection. For projects that are going to go out to 2070, which you would end up using between 21 and a 40-inch sea level rise projection for. Next slide, please. The NOAA high curve, which highlights that is above that blue shaded range. These are for infrastructure that are greater than 50-year life cycle, or may have rather significant impacts, and that you have a very low risk tolerance for. So the examples given here are an airport, a nuclear power plant, a bridge, or a wastewater treatment plant. Because of the long life cycle of those different types of infrastructure and the critical nature and the absolute lack of adaptability of moving those locations, you would want to use a curve which is more conservative, and that would put you at the NOAA high curve. The final curve on the compact's projection is the NOAA extreme curve. And as several of the speakers have noticed, the idea of providing this curve was to give the audience an understanding of what the upper range of possible sea level rise would be under catastrophic ice sheet failure. And it's really only put there for informational purposes. Generally speaking, you would not use this curve for planning purposes. Dr. Danchuk has already pointed out that as part of this guidance document, we have not only provided you with the absolute range of how sea level will rise, but we've also provided the information to the NAVD datum. And since she's covered that, we're just going to keep moving on beyond that. How do you choose a reference elevation? One of the great things about the progress that's been made in sea level rise science and in using sea level rise as a planning tool is that we have so much data available to us that is on the internet and can be tied to interactive applications that are on different websites. And so as Dr. Obasekera pointed out, there's a number of long-range tide gauges that are available in the South Florida region. I've listed a number of them here, but for example, the Lake Worth Station has been here since 1996. There's a brand new tide gauge in Southport Everglades that was established in 2018. That particular tide gauge you could not use to look at long-term records, but it's good to know that it's there. Each of these different tide gauges has an interactive page on the NOAA website which provides you with a conversion table for the different datum so that you can easily convert from mean sea level to NAVD to mean higher high water. And it's very important to know that those are out there, so that if you only have the information for your location in one datum, you can determine how to convert that information to a datum that is useful to you as you are trying to understand how you're going to use these sea level rise projections. There's also a number of great tools out there that you can use that actually provide a calculation to those individual tide gauges and coming back to a custom calculation to the NOAA curves, or that can help you visualize site-specific sea level rise projections, or can visualize the inundation of a specific location based on the NOAA curves. So we're going to show you that very briefly. The first one is the U.S. Army Corps of Engineers Sea Level Change Curve Calculator. This particular graphic is tied to the Vaca Key tide gauge, and it's a very simple tool. It allows you to pick the tide gauge that you want to connect to, the time frame that you want to look at, and as you can see from the table on the right-hand side of the graphic, it gives you the actual values in 5-year increments of the projected rate that you will see for those various curves, which is very useful when you're trying to figure out which of these curves and what's the actual data what's the measurement that I'm going to tie to for a given year, depending on which graphic I'm going to use. Very useful tool. The Army Corps also provides a very different tool, which is the Sea Level Rise Tracker. And you see two graphs on your screen. And you'll notice that in the lower left, there's a blue shaded bar. That blue bar allows you to determine the beginning and end of the projection that you're looking at. And so this particular projection looks out to 2015. On that same website, you can then slide that bar so that you can look out to, for example, the year 2080 and see what the actual values are for those different projections at the location that you're interested in. And so this tool allows you to visualize on a different time scale what different scenarios will look like at very specific points in time using that slider bar on the bottom. And the last tool I'm going to talk about is the University of Florida's Sea Level Scenario Sketch Planning Tool. So this is an area in Fort Lauderdale. You can see that there are areas that look like land, but it's covered in blue or red. And what that is showing us is areas that are potentially inundated using a very specific scenario. So there's a box on the right-hand side that talks about which projection I'm using in this particular scenario, the NOAA intermediate high. The time frame given is 2060, and the graphic that you're seeing is those inundations at that sea level rise curve during that time period. So it's a very useful tool to help visualize and understand how the various curves actually play out in terms of inundation at a given site location, which are very useful if you're trying to choose sites that would be more resilient and less vulnerable to sea level rise moving forward in any given scenario. So as I mentioned, on June 25th, there is a dedicated webinar that will be talking exclusively about how to apply these projections. And I encourage you to explore how to use them and absolutely apply them to the projects that you're working on as you move forward in building and constructing infrastructure in the South Florida area moving forward. And with that, I can entertain questions, Lauren.
Great, thank you so much, Dr. Gossman. So to that point about application, someone has commented that seepage may occur no matter how high we build our seawalls here in Southeast Florida. So what are our realistic options to protect the coast in terms of seawalls? And also, how are we starting to think about materials, given that we know that seawater can affect the types of materials that are being used within infrastructure and seawalls in particular. Are we looking at new types of materials that might be longer lasting or maybe more sustainable?
Okay, so there's two questions there, one on seepage and one on materials. So on the question of seepage, there are absolutely going to be locations in the South Florida region that are not going to be able to be hardened or protected by certain types of different types of infrastructure. And so there's a lot of discussion about elevation of certain land masses, but we have to remember that the community of 50 years ago is not going to be the community of 50 years from now, and that there will be areas that will have to transition to different land uses than the current land uses as sea level continues to rise. We don't have an engineering solution to all of those issues. In terms of materials, I'll give a quick example from the city of Fort Lauderdale. We're currently replacing a significant portion of our wastewater force main. The previous materials that were used were ductile iron. And ductile iron has two vulnerabilities to sea level rise. Number one is the pipe itself is very rigid. And so the joints are subject to the forces of rising and falling groundwater, which can work the joints apart. And the material itself can be corroded by salt water. And so the city is using HDPE pipe to replace that previous pipe, which is a thick-walled plastic pipe that can move more easily, and its joints are less subject to that movement because the pipe itself can flex. So material choice is very important moving forward, especially for underground infrastructure as we move forward with applying these projections.
Great. And maybe somewhat in the same vein, you talked about, you know, the use of the curves in planning for critical infrastructure. So can you talk a little bit more about how you see the use of the projection in sort of in supporting the movement over time of hazardous facilities away from the coast or other high value infrastructure like fuel storage, waste management, the siting of power generating facilities, and the role of the projection in helping to ensure these facilities are not sited in highly exposed regions?
A great question. Early on, the compact developed a vulnerability analysis and was looking at critical infrastructure that was currently existing that would be vulnerable to sea level rise. And so I think that all future planning projects should be considering the projections in siting. You can't necessarily move existing facilities, but new facilities, we need to plan to have them be in higher elevation locations. And we do need to do some planning for those existing facilities that are threatened that may require some significant intervention in order to protect the environment from whatever may have been stored at those locations.
Absolutely, great. I think with that, we might be out of time for additional questions to make sure that we close on time, although there's two that came in that I will answer directly. One is, are there real case studies of how projections have been used in a project? For example, engineers using projections to design a specific project. I'll just say that the entirety of our next webinar is going to be focused on world case studies of successful application of the sea level rise projection, how it's been used in projects, policy, planning, design, all of those things. So we have a myriad of really great examples. So I encourage you to tune in for that. And then another question that came in is, are material recommendations included in the guidance document? And no, we don't have material recommendations in the guidance document, but I think that's a really great suggestion and thought, and certainly the compact will take that into consideration for future guidance products. So with that, I just wanted to thank Dr. Gassman again, to understand step by step how to actually use the projection guidance. So thank you for your expertise and sharing your presentation with us today. I want to close out today's webinar session by just thanking again all of our speakers, as well as everyone who has joined us today in the audience for your interest and your participation and great questions, as well as the work that you all are doing to build community resilience to climate change. As a reminder, our next webinar in this series is taking place next week, a week from today, Thursday, June 25th, from 10 a.m. to 12 p.m. Eastern, where we're going to hear, as I just mentioned, about a myriad of local examples of best practices and successful implementation and applying the projection in Southeast Florida. We also received a bunch of questions throughout today's webinar, sort of related to policy making practices in response to sea level rise. That will also be covered next week. And we also heard some comments and questions related to the integration of equity into adaptation efforts related to sea level rise, and how we do better about communicating on sea level rise and breaking down silos between local government and the public. These are all really important topics, and they are going to be covered in much more detail in the third webinar on July 1st. So thank you for those great comments and questions. If you registered for this webinar, you are automatically registered for the next webinar in the series. A recording of today's webinar, as well as the presentations that were shared, will be posted on the Compact's website on the implementation workshop event page in the next coming days, and it will be shared with all registered participants of this webinar via email as well. We very much look forward to your participation in next week's webinar, and we wish you a wonderful day. Thanks for being with us.